All right. Hello, Senior Math. Today we have our Unit 4 assessment review over permutations, combinations, binomial distribution, Poisson distribution, because our assessment is going to be next Tuesday. So your assessment over this is next Tuesday, so we're going to review today. This assessment will fall in the fourth 9 weeks. So once again, and then 9 weeks is Wednesday. What is that, the 25th or something like that? 25th, 26th, whatever date that is. So we're going to be reviewing on your assessment's going to be on Tuesday. It's going to fall in the fourth 9 weeks, so you have time to retake. And so we're going to be reviewing today in order for preparation for that assessment. So once again, we're going to cover permutations and combinations, binomial distribution, and Poisson distribution are the three things that are going to come up on your assessment. All right, so differences between permutations and combinations. So we learned about two ways of arranging items, and there's two types of ways we could count arrangements. It has permutations, where order matters and each order is separate, or permutations, where order does not matter and any sort of grouping can be the same, assuming they have the same elements in them. So for example, permutation, if you had the group 1, 2, 3, 4, that's different from 2, 3, 4, 1 because the order is different. Well, if you had the combination, 1, 2, 3, 4 would be the same as 2, 3, 4, 1 because the order did not matter. So they are the same combination because the order that you put those numbers in does not matter as long as you have all of them in the same group. So we're going to look at a few examples here. We're going to see if we can first figure out whether it's a permutation, and then we're going to try to solve the question using our Desmos calculator. So are these problems permutations or combinations? So how many ways can you award a first, second, and third place medal to 15 competitors? So the first thing you have to think, does order matter or does it not? So order does matter. It matters who gets first, it matters who gets second, it matters who gets third. Those are different valued places. And so this would be an example of a permutation because order does matter. And so we know, if we think about it, it's like our NPR, and then we have our parentheses and then the comma over two things. The first number is always the total group. So we have 15 competitors. So there are 15 possible people to be awarded. And then we're handing out 3 different medals. So we'll do NPR 15, 3 into our calculator, and that's going to be our solution. So once again, in order to get it, we can pull up Desmos, go to functions on the calculator, go over to stats, and then there is NCR and NPR. This is going to be our combinations and our permutations. So we're doing a permutation. So we're going to do 15, 3, and we get 2,730 different combinations. So next we have how many different groups can how many different groups of 4 can you form out of 20 students? So if you have 20 different students, you want to form groups of 4. Now it doesn't matter if in the first group, doesn't matter whether Susan was chosen first or Joseph was chosen first. They're both going to be in that first group. So in this case, order does not matter because as soon as you get in that group, you're all in the same group. You all have the same task. It doesn't necessarily matter what order you were chosen to be in that group. So this is going to be a combination because order does not matter. Combination. Because it's a combination, we know we're going to do NCR. We have a total number of 20 students, and we are choosing 4 students at a time. So we're going to do, next line, we're going to go to functions, NCR 20, 4, and that gives us 4,845 possible combinations. All right, last question. How many different hands can you be dealt in Texas Hold'em? So if we think about Texas Hold'em, you're dealt 2 cards out of the deck, which has 52 cards. Now, when you're dealt those 2 hands, it doesn't matter if you're dealt the ace first or the jack first. You still have an ace and a jack in your hand. You could have been dealt the jack first, then the ace first. It doesn't matter. So this is a combination. Once again, because order does not matter for this one. So it's a combination. You're dealt 2 cards out of 52. So, sorry, not NPR, NCR. So our NCR for this problem is going to be 52, comma 2. It's the total number of items, and then comma the number of items you want to select. So 52, comma 2. Out of 52 items, we're choosing 2. So last one of these, NCR 52, comma 2, and that gives us 1,326 possible hand combinations. Assuming you're using a normal deck and you're dealt 2 cards. Sorry, that's supposed to be a comma, not a. There we go. All right, so that's permutations, combinations. That's pretty the gist of it. Just being able to plug those in. Now, we did have more complex problems because we could use this to help find the probability of certain events. And this is what you sort of did your little activity on, where you were trying to find probability of like different hands of poker and things like that. So we had these complex permutation combination problems that dealt with probability. So compute the probability of randomly drawing 4 cards from a deck and getting exactly 1 ace. So dealt 4 cards, getting 1 ace. So we know probability is desired outcome divided by total outcome. So I first need to think, what is my desired outcome? Well, my desired outcome is to be dealt 4 cards and get 1 ace. So one of those cards exactly 1 ace. So one of those cards needs to be an ace. So I know there's 4 aces in the deck. It doesn't matter which one I get. I just want one of them. So thinking about NCR, that's going to be 4 out of 4 aces. I want one of them. So that's going to be my first card I get dealt. Now, thinking about the other cards, how many other cards are there in my deck that I could possibly get dealt? And these are all combinations because, once again, if you're dealt an ace and then a 2 and then a 3, it doesn't matter if that's the same thing as getting dealt a 2, a 3, then an ace, because it doesn't matter once they're in your hand, they're in your hand. You can rearrange them however you want. So if I think about the other cards in the deck, I have my ace now. So all the other cards in the deck, there are 48 other cards in the deck that I'm hoping to get because I don't want any more aces. I want exactly 1 ace. And so out of those 48 other cards in the deck, I need 3 more because we said we're getting dealt 4 cards. So I have 1 ace. I need 3 other cards out of those other 48. That's my desired outcome. That's my desired outcome of getting 1 ace and 3 other cards. Well, my total possible number of outcomes, once again, this is all combinations. My total possible number of outcomes, I know there's 52 cards in the deck. I'm getting dealt 4 of them. So this is going to be my probability. It's going to be NCR of 4, 1 times NCR of 48, 3. Because once again, this is my probability of getting an ace. This is my probability of getting those 3 other cards that aren't aces divided by my total number of hands possible. So we can go over here. We can type this all at the same time. So I'm going to put parentheses around the top to make this a little bit easier for myself. I'm going to do functions NCR 4, 1, close my parentheses, times NCR 48, 4. That's my getting, or 48, 3. I'm sorry. That's getting dealt my other cards. I guess my parentheses didn't really stick together. Let me get rid of these. There we go. And then all divided by NCR 52, 4. So we look at that, we get 0.256 as our probability. I'll round to 3 decimal places. 0.256. So roughly over 25% chance of getting an ace. Exactly 1 ace. All right. A slot machine has 3 reels that all have 20 different symbols on them. Each reel shows 3 symbols at a time for a total of 9 symbols shown. In order for a player to win, the same symbol must show up in a line on all 3 reels. This can be diagonally, up and down, vertically, whatever. If each reel has 1 jackpot symbol, what is the probability of winning a jackpot? All right, so for those of you who don't know, it's kind of like you have your 3 reels that each show 3 numbers at a time. So let's say this is reel 1. This is reel 2. And this is reel 3. Your goal is to get a row of jackpots. So that could be, this could be 1 row. This could be a row. This could be a row. This could be a row. or this could be a row. So that's a total of five possible rows, if we think about it. There's 5 possible options. So if we think about our probability of getting a jackpot, we know the desired outcome is there's 5 possible combinations. If I randomly just pull this lever if I randomly pull this lever 3 times, there's 5 possible combinations that are going to give me a jackpot. If I get a jackpot on all these 3 top ones, if I get a jackpot in this one, if I get a jackpot here, there's 5 possible combinations. Well, how many total possible combinations are there, though, in order to calculate this? Well, if I think about this, in my first option, when I pull that lever, there are 20 possible numbers that can show up, and they can show up in all those different spaces. There's 20 possible numbers for each of them. So that is 20. And the second reel also has 20 possible symbols, and then the third reel has another 20 possible symbols. So there's 20 possible symbols that are going to show up in each of these 3 spaces. So out of the 5 possible options, 20 times 20 times 20 is the total number of probability, because there's 20 symbols for this combination, there's 20 possible symbols for this one, there's 20 possible symbols for this one, and so that's going to be our total. So 20 times 20 times 20, or it's 5 divided by 20 times 20 times 20, gives us 0.000625, which comparatively to some like jackpots, like the lottery or something like that, it's not that bad, but there's not good odds. And no means is that good odds. It's less than a tenth of a percent. All right, so that was our complex permutations and combinations problems. Moving on, we also talked about binomial and Poisson distribution. So with each of these, we had to use those charts. So you need to have those charts. I will print some off for those of you who are here, so you can use them, have a hand printed version. If you want to print them off at home as well, go for it. I would recommend it. It might be easier for that, but you can also use the ones that are on the computer. I will post them on there as well. So let's look at this binomial distribution. So you would need your binomial distribution chart for this one. So the 10-year survival rate for pancreatic cancer is approximately 50%. If 20 people who have pancreatic cancer are properly treated for the disease, what is the probability that exactly 10 will survive for 10 years? So we know with binomial distributions, there's 3 things we need to know. We need to know what is the N, what is the P, and then with each problem, we're going to have a different K or R, depending on what you're looking at. I guess we learned it as R. So what is the R as well? So you have a P, an N, and R. So N represents the total number of people that are in the survey, or total number of people that you're looking at, or total number of options you're looking at. In this case, there's 20 because we have 20 people with pancreatic cancer. We're looking at the probability of surviving. We know that the 10-year survival rate for pancreatic cancer is approximately 50%. So 50% is going to be 0.50. And then for our very first question, we're looking for exactly 10 people. So we're looking for the probability that X equals exactly 10. So we know we're going to look in the 20 row, or we're going to look in the 20 section, N equals 20, and then we're looking at P of 0.50. So pulling up our binomial distribution, we're going to go all the way down to 20. N equals 20 should be the last part. And then my 50 row is down here, so I'm going down in this row. So I'm using this column right here, up and down. And then I'm looking at N equals 10. So I'm going to put my finger on this column. N equals 10, or K equals 10 is going to give me 0.176. 0.176 is going to be our probability, because we know when it's exactly, I just have to write down whatever the number is. So 0.176, and we're done. So let's look at the probability at least 5 people will survive for 10 years. So probability that at least 5. So the minimum value is 5. So X needs to be greater than or equal to 5, because the lowest possible number is 5. Well, if I think about it, X is greater than or equal to 5. Well, what numbers are greater than or equal to 5? 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Those are all numbers that are greater than or equal to 5. So essentially for my problem, I would have to take from 5 and add all those numbers up in this row all the way down to here. Now that's a good number of numbers to add up. But if I look, some of the ones at the end are 0, so they won't change too much. But I would have to add all these up. Well, we know another way of solving this question. We can do the inverse or the complement of the event, the opposite. So we can do 1 minus the opposite of the thing happening, because we know probability is always a total of 100%. So if we do probability of x being less than 5, 1 minus the probability of x being less than 5, that's the exact same thing. Well, what is the probability of 1 minus probability of x being less than 5? Well, what numbers are less than 5? 4, 3, 2, 1, 0. Those are all numbers that are less than 5. So rather than adding up all of these, I can go backwards. I can get 4, 3, 2, 1, 0. And if I look at a couple of these, most of those are 0. So really it's 0 plus 0 plus 0 plus 0.01 plus 0.05. So I have 0.00 plus 0.000 plus 0.000 plus 0.00. Sorry. I forgot my 1 minus. It's 1 minus 0.000 plus 0.000 plus 0.000 plus 0.001 plus 0.005, which is just in total 1 minus 0.006, which equals 0.994. So our probability that at least 5 people will survive is fairly high. It's like over 90%. All right, last question. At most, 6 people will survive. So at most, when we say at most, that means the highest possible number for x is going to be 6. So x needs to be smaller than, less than, or equal to 6, because the highest possible number is 6. Well, that means I just need to take the numbers 0 through 6 and add those together, because numbers that are less than or equal to 6 are 0, 1, 2, 3, 4, 5. Well, luckily, I already have the numbers 4 through. I already know the numbers 4 through 0 through 4 are this number right here. So I know it's going to be 0.006 plus whatever the probability of 5 is plus whatever the probability of 6 is, and those would be my numbers. So these are the numbers 0 through 4. Here's 5. Here's 6. So 0.015 plus 0.37. 0.015 plus 0.037. If I add those to my 0 through 4 that I already calculated from the problem before, this gives me a total of 0.053, I believe should be the correct answer. And that would be our probability of at most 6 people surviving. So very unlikely, only less than 20% chance, or less than like a 1 in 20 chance that at most 6 people will survive. So that was our binomial distribution. Our Poisson distribution, we pretty much did the exact same way, except rather than with Poisson distribution, they told us something the n and the p. With Poisson distribution, they give us the average, which was represented by this letter mu. But in the symbol on the chart, I don't know why they have lambda there. Most people use this. But so we need to know the average. So in a food processing packaging plant, there are on average, 2 packaging machines break down per week. What is the probability that there are no machine breakdowns in a given week? So we are looking for probability of x equaling 0. So we know the average is 2. So that means on our Poisson distribution chart, which looks like this one, we need to find 2. So the whole numbers are typically always on the right side. So 2 is going to be, that's 3. That's 2. Okay, so here is 2. So we're using this row, this right-hand column over here. That's going to be our distribution. So we are looking for that there is no machine breakdown. So we know on average there's 2 machine breakdowns. In this case, there's no machine breakdown. So that's x equals 0. So we're looking for x equals 0. Well, x equals 0 is this top row. So we are looking for this last number right here, 0.1353. We know because it's x equals, we just have to write down the number down. Anytime it's exactly a certain amount, we just write the number down and we're done. It's only when there's less than or greater than this we have to worry about. All right, last question. Calculate the probability that there are no more than 2 machine breakdowns in a given week. No more than 2 machine breakdowns in a given week. So no more than means that we're hoping that the numbers are less than or equal to 2. No more than means the max amount can be 2. So the probability that x is less than or equal to 2, once again, this means the probability that x is all those numbers that are smaller than or equal to 2. Well, what numbers are smaller than or equal to 2? 0, 1, 2. Those are all the numbers that are smaller than or equal to 2. So I just have to take those 3 numbers and add them together. So if I look at my numbers that are less than or equal to 2, I have 0, 1, and 2. And I can add those 3 numbers together. So these first 3 in this row here. So 0.1353, 0.2707, and 0.2707. Once again, sometimes you might get the same number show up twice, and that's okay. So 0.1353, 0.2707 plus 0.2707. We add those together, and a probability that there are no more than 2 machine breakdowns in a given week gives us a total probability of 0.67. So there's like a 2/3 chance of a machine breakdown, of at least, or of no more than 2 machine breakdowns in a given week. Pretty good odds. Hopefully you don't want more than 2 machines breaking down. So that's our binomial Poisson distribution and combinations, permutations. You'll have a little bit of a review over all these different subjects right now to work on for this period, and then a little exit slip just to prepare you for that assessment once again, which is going to be on Tuesday, but it will fall onto the 4th 9 weeks, so you will have time to retake it. It's not going to be like it's going to go under gradebook and like change your grade right before the end of 9 weeks. So it will fall on the 4th 9 weeks, so you have time to retake it in that 4th 9 weeks if that is the case. That's where we're going to wrap it up for today. Let me know if you have any questions, and you can get started on your review.